chapter 7 mainly talk about forces in beams, but they do have another topic, which is called the forces in cables. So I'm going to briefly talk about this one. It's basically the special thing in chapter 4, but we just need to identify one more question. Okay? So you can frequently see a lot of cable problems, in fact. Okay? So obviously there's one person walking on the very, very slender cable, okay? And then if you want to calculate the strength or you want to calculate the force in the cable, then this is something you can do just based on our current chapter, chapter 7. Okay? Now, simplifying that scenario, we are basically talking about something like this. Okay, so for example, you have a cable. I didn't give you the whole picture. Most likely this cable somehow clamp over here, the other end clamps somewhere here. So then what I'm trying to say is, okay, you do have a cable A, C1, C2, C3, B. So cable AB, okay? So this is the cable AB, and then on the one side is the pin end supported, and the other side is another pin end supported. This cannot be rollers, by the way, okay? Because this going to give you the restriction in any two directions. That's why both are pins. Okay? In addition, there's some kind of concentrated load acting in between. Okay? So now, how are we going to calculate the reactions, and how are we going to calculate the cable force? Talking about the cable force, then you're going to make some cut. Okay? But before talking about the cable force, which need to be calculated by cutting somewhere, let's first probably need to calculate the reactions. And we know that in chapter 4, or even in chapter 7, in chapter 6, how are we going to calculate the reactions? That's supposed to be simple. We just cut those reactions, right? We cut point A, we cut point B, and we plot the free body diagram. Okay? Let's follow what we have learned. So this is the cable AB again. But we cut point A, we gave two reactions, right? So these reactions are called AX, AY, which are unknowns. We know that. And then we cut point B, which is another pin, and then we gave another two reactions. Okay? And assuming we know these forces, let's just put those forces here. Now, this is what we call the free body diagram for the entire structure. The question is, for any given this kind of two-dimensional, you have to agree that's two-dimensional, right? How many equations we're supposed to generate? We can generate 3. Okay? If you go back to look at chapter 4, right? We always talk about the independent governing equations or equilibrium equations for two-dimensional problems are 3. 2 force equations plus a moment equation. But now, when you look at this free body diagram, how many unknowns do we have? This time we have 4 unknowns. Okay? So, obviously there is a challenge in general. We cannot have enough equations. We want 3 equations, but we have 4 unknowns. Okay? So if you were encountered this kind of problem before, then the simple way you can say is, let's give up. Yeah, we don't know how to do it. But now this time, I'm just giving you a trick, because that's specifically for cables. It does not work for beams. It's for cables. For cables, you can in fact generate another equation. And in fact, that's also the special case as we talked about before in chapter 4. That's called the 2-force body problem, in fact. The reason is this. At anywhere you want to cut, for example, right? At point D, you want to cut. You want to cut. At point D, after you cut, there is no moment at that point. If there's a moment, internal moment, you typically want to have beam. For example, going back to look at any picture you had in chapter 7, right? When you have a beam, when you cut it, then after you cut, you need to give an internal moment. That's called M. But if this is a cable, there's no internal moment because it's very flexible. So that's why when we talk about cables, I highlight here. Cable is flexible. In other words, namely, resistance to the bending is very small. Very small means you ignore it. Okay? So at any point, if you want to make the cut, then let's say we cut point D. Once we cut point D, the whole structure is split into 2 parts. You pick whatever part you like. For example, we're going to look at the left side. Okay? We're going to look at the left side. When you look at the left side, we have still A here. You have an AX, AY. Okay? And you cut here, which is to the right of C1. Then you still need to give at C1, there's a force P1. Just put it here. Now you cut it at point D. Once you cut at point D, there's an internal force. Obviously, that's right. But the internal force is going to any direction you like to say. However, there's no internal moment. Okay? And actually, you know what? This one, it has to be, is a two-force body. It has to be going through that direction. So now, let's going back to look at this new free body diagram. This new free body diagram. New free body diagram. How many unknowns do we have?
3.
We have 3 this time. See? 1, 2, 3. So we can still have 3 equations. Especially, you can collect all the forces in y direction set equals 0. You collect all the forces in x direction equals 0. And then you take a moment equation. For example, you take a moment equation at point D, or you take a moment equation at point A. Then you can solve for these unknowns. So that's why after we make a so in principle we have 4 unknowns. There's no way, because we only have 3 equilibrium equations for the entire structure. That's why it is not sufficient to determine all the reactions. But that's fine, because this is the cable problem. Then what we are going to do is we're going to create additional equation. So that additional equation can be obtained by considering an equilibrium of part of the cable. For example, point D, you cut a D, you look at AD part. Of course, you can look at the DB part, not a problem. Just look at one part. And then after you make the cut, there's no moment at point D. So that's why you can take a moment of all forces at point D, then there's one equation, and then you collect all the forces in x direction, you collect all the forces in y direction. The bottom line is you can calculate all the unknowns. Okay, so this is the principle to solve any cable problems. Now I'm going to just give you an example, just to show you specifically how we can solve specific problem. We have a cable like this. Okay, you can think about this kind of like a cable car, right? If you travel to Palm Springs, you basically see this. Of course, this is very simplified. At point A is pin support. At point E, there's another pin support. All the geometries are given. Okay. In addition, there are 3 forces, concentrated load. It's like a tram or cars located in different areas. Then we need to calculate the reactions. We need to calculate the cable forces. Okay. So geometries are pretty much given. So cable AE, the whole thing, support 3 vertical loads. 1, 2, 3, with a given 6 kips, 12 kips, and 4 kips. By the way, kip. 1 kip is what? It's 1,000 Newton, 1,000 pounds. Okay. So cable AE supports 3 vertical loads from the point indicated above. If point C, see this point C. If point C is 5 feet below, 5 feet below this, the left support. So this is the horizontal line. It's called the left support. For example, it is 5 feet below. So from here to here is 5 feet. Then we can determine the elevation of point B and the point D. So what is the elevation of this one? In other words, this one. And what is this? Okay. So in other words, the elevation of this, you don't have to know it. You can calculate. Of course, we should be able to calculate the reactions as well. Okay. So typically, for this kind of problem, if we know at one point, we know the location. In other words, we know at point C that's 5 feet below, then what we're going to do is a cut at that point to generate one additional equation. So we cut it at point C, then the whole structure is split into 2 parts. You pick whatever part you like. Let's pick the left side. Okay, so again, I'm sorry. So again, you look at the entire structure, you cut it at point A, you gave 2 reactions, you cut at point E, you gave 2 reactions. There's no way you can solve for 4 unknowns because there are only 3 equations. That's why we're going to cut at point C. So once we cut at point C, we look at this part, A, B, C part. So then what we're going to do at point A, again, you have 2 reactions. Point B, you still have this one. At point C, you cut here, you gave additional force. But you also have this 12 kips acting on point C, right? So this is what we call a free body diagram on this part. Then what we're going to do is to calculate the reactions first. How to calculate reactions? Well, there's many ways because you have 3 equations anyway. You can use whatever you like. For example, we want to collect the moment of all forces at point E. Where's I'm sorry, not this one. Look at this point C. So let's take a moment at the point C of this structure. Take a moment at point C. These 2 forces will not be involved. That's fine. But you have AX. So AX times the shorter distance from here to here. That's a shorter distance. AX times shorter distance 5. AX times 5. and this is going to be clockwise on this rigid body, right? So that's negative. So this is the moment due to AX. And then what is the moment due to AY? So that's going to be AY times the shorter distance from C to here. That's going to be 10 plus 20, 30. So 30 times AY is also clockwise. So put a negative sign here. So this is the moment due to AY. And then what is the moment of this force at point B, which is, what is the 6 kips, right? So 6 kips times the shorter distance from here to here, or C to here, that's 10. So 6 times 10, that's the moment, but this is a counterclockwise. That's why you put a positive sign. So this is the equation you can generate based on the moment at the point C. This is the one equation. You can easily write down other 2 equations by collecting all the forces in X direction, all the forces in Y direction. However, if you want to go back to look at the original overall, what we call the overall structure, then even though you have 4 unknowns, but if you want to take a moment at this point E, then you are only going to have AX, AY involved in that equation. If that's the case, you can combine these 2 equations to solve for the 2 reactions, AX, AY. So let's take advantage of this overall free body diagram and take the moment of forces at point E. EY, EX will not be involved because they are going through this point, but you have the moment due to force at point D. That's a 4 times this one with a 15. 4 times 15 is counterclockwise, so you have this term here. And you have a 12 kips multiply 15 plus 15, 30. 12 times 50, 30, that's also counterclockwise. So 12 times 30, that's another moment due to this. And you have the moment due to this for 6 times 40. So 6 times 40, and also counterclockwise. And finally, you have the moment due to AX. That's going to be counterclockwise, AX times a 20-inch. So AX times 20-inch, that's a moment due to AX. And you also have AY times this shorter distance, 20, 10, 30, plus 30, 60. So 60 times AY. But this is a clockwise. So that's why you have a negative sign. So you are simplifying this equation, you end up with this. This one need to combine with another equation we just generated, these 2 equations, to solve for AX and AY. Right? So from AX and AY, you can basically calculate, from these 2 equations, you can basically calculate AX, AY. Now, after you get AX and AY, can you calculate EX, EY? That's not a problem. We did not write here. But obviously, that's not a problem, right? Going back to look at this entire free body diagram, you need to collect all the forces in X direction. In X direction, what is the EX? EX equal to negative AX, correct? Because there's only 2 forces in X direction. If you want to calculate it, so AX is finally given negative 18. Negative 18 means what? Negative 18 means AX is in fact to the left with a magnitude called 18 kips. What is AY? You calculate AY, which is 5 kips. That means AY is going up, but the magnitude is 5 kips. So if this AX is to the left with 18 kips, then what is the EY? EY is going to be to the right with the same magnitude, 18 kips, because there are only 2 horizontal forces involved. Now, you know AY, which is 5. So this is the 5, but going down 6, 12, that's 18 plus 4, 22. So all 3 forces going down 22, 1 force going up 5. Then what is this force? This is going to be 22 minus 5. 22 minus 5. 22 minus 5. 17. Right? So EY is going up. The magnitude is 17. So the bottom line is you do need to create a new equation in order to solve this original problem. And that new equation is basically you need to make a cut at a certain point which you know the location so that you can generate this moment equation. Okay, so that's the first part. We calculated the reactions. Now, the question asks us to calculate the elevation at the point B and the elevation at point D, the location, but with given forces. So next one, what we're going to do, but this time we already get those AX, AY, EX, EYs, right? Next time, we need to calculate the elevation at point B and the elevation at point D. So let's say we have this part, we cut it at point B, because you want to calculate the elevation, you have to cut at point B. Once you cut point B, you look at the left side, you have AX, AY, which are calculated before. And at this point, you cut here, you got a BY, right? So how to calculate BY? So basically, you just take a moment at point B. so that you don't need to worry about this cable force. Of course, if you need to calculate cable force, you need to use additional two equations. If you only need to calculate the elevation, then take a moment at point B. So now these two forces are not being involved because both of them are passing through that point. So basically you have 5 kips. So 5 kips times 20. 5 kips times 20, that's clockwise, so there's a negative sign here. And then the moment due to this 18, so 18 times YB, because that's elevation. And that's counterclockwise, so YB times 18. And minus this moment due to this force, that's supposed to be 0. And from this equation, you can directly calculate YB. So YB, based on your calculation, is negative 5.56. Negative 5.56, that means what? This one actually is going up. Let me see. Wait, I'm sorry. I don't like to write this way. Okay. From this equation, in fact, YB equal to positive 5.56, I believe. Because here, this one times this minus this one equals this. This YB, in fact, is what? YB, in fact, is a positive 5.56. But I know the reason why they put a negative sign, because they want to indicate it's below that. But the reason you cannot get a negative because you assume this YB is below already. Right? Because the YB you plotted, point B is already below point A. So that's why this YB, based on your calculation, should be positive. If it's a positive, then in fact it's below. So that's why their final answer is a negative 5.56. Means point B is below point A, and the distance between A and B in the vertical direction is positive 5.56. The distance. But we're talking about elevation is supposed to be going down. So that's why they finally put negative 5.56. But what I'm trying to say is these two things are not consistent. Okay? Anyway, so this is the final answer. Similarly, you can also calculate elevation at point D. So we need to cut at point D. Now we're looking at this one. So this time we assume point D is elevated up, and that's dy. So same thing, you are going to collect the moment. There's a mistake here because that's supposed to be the moment at point D. They forgot point D here. That's supposed to be at D. Because you take the moment of all forces, you need to give they were written here, right? It's not written here. So this is D. Okay, so moment at point D. So then these two forces will not be involved. You have this 18. So 18 is going to be clockwise. 18 times dy. 18 times dy is clockwise. And then 5 times 30, 45. 5 times 45. 5 times 45. That's going to be clockwise. That's why negative sign. This one is 6 times 25. 6 times 25 counterclockwise. That's a positive. 12 times 15, which is also counterclockwise positive. From this equation, you get YD. So YD, because we assume going up, and from this equation, you calculate positive. So that's why the elevation is positive 5.83. Any questions? So this is basically the typical cable question. Your strategy is to create one more equation. And that equation is obtained by making a cut at a certain point. You know the location. For example, like this one, you need to cut at point C. Because the point C, they gave you the location, which is 5 feet below. That's why you need to cut point C. You will say, can I cut anywhere else? You can cut it, but you won't solve the problem. Right? So that's why it's useless. You just have to cut at point C, because at point C, you happen to measure the distance, or called the elevation. And once you know that, you can make the cut, and you can solve the problem. Okay? So this is the first part I call forces in cables. And all you need to do is to generate one more equation. That's a moment equation after you make the cut.